Hello, my name is Junhong Fang. Today I would like to present our work, PeloPartition, Proving Blockchain Resilience to Network Partitioning. This work is done by me, Fazal, and others from HLab in University of California, Irvine. The talk is organized with following sections. First, we will discuss the background and motivation of PeloPartition. Then we will show how PeloPartition solved the problem. Next, we'll discuss some threats that can affect the integrity of the ledger. And finally, we will evaluate our work and compare it with some traditional blockchain like Bitcoin. The most exciting thing about blockchain is that the whole world agrees on the same chain without relying on a single point of data source. Everyone can participate in storing and writing data, but still can reach global consensus. However, it relies on the globally connected network, and the design of the blockchain cannot tolerate a global scale network partition. So imagine a solar storm breaks the submarine cable between America and other continents. The network will be partitioned into two regions, and America cannot communicate with others. As a result, a fork will happen in blockchain, where America has its own branch and other continents will work on the other branch. So what happened after networks is recovered? Branches from two regions will be broadcast to each other, but because of the longest chain rule of blockchain, only the longer branch will be considered the main chain. The shorter branch just disappear, meaning all transactions happen during the partition are not recorded. In the example, we only see one block from the shorter branch being dropped, but what if the network partition lasts for a longer time? 1 week or even 1 month. Lots of transactions just disappear, while most of them are already considered committed and the actual trades already finished. Now we will talk about the system design of PeloPartition. The goal of our system is to preserve all progress during a network partition. It is done by designing a blockchain that supports splitting and merging. It also needs to ensure the integrity of the ledger. For example, make sure that there is no conflicting transactions. We carefully analyze the new threat introduced by our new design and provide solutions to them. We adopted a design from Basecoin that combines Byzantine fault tolerance (BFT) with blockchain for stronger consistency. The main idea is that every new block will be verified and signed by a dynamic consensus group. The new block will be considered committed once being signed, without waiting for several blocks after it. In Basecoin, the group is formed by miners of previous W blocks and the miner of the new block itself. Here, the window size W is 3, so block D will be signed by 3 previous miner, A, B, C, and itself D. We use the signature as a global recognizable identifier for the status of network. We'll see how to do that in the next slides. When a network partition happens, the new block may not reach everyone in the consensus group, so it will be signed by only part of the group. When a block with less than W miner is published, every node in that region knows that the network has been partitioned, and they can identify which branch they are working on with the signature of that block. Also, the hash power of that region can be estimated with the number of signers. For example, miner ABE year after partition, they are in one region, and miner E mines a new block, capital E. The consensus group of E should be B, C, D, but now it can only reach B. So block capital E will be signed by only B. Now ABE can identify their branch with the signature of block E, and the branch size is 1, which has 1/3 of the consensus group. In this way, the chain will be split into branches after partition, and each region will have exactly one branch. To merge multiple branches after the network recover, we introduce a merging block that can have multiple parents. After network recovered, miners can receive all branches, and they will create a merging block that points to each of the branches. The consensus group is selected from each branch according to the branch size. Here, merging block A points to both branches. The size of the upper branch is 1 from the previous slide because the first block only has one signer. So we pick 1 minor B. Similarly, lower branch has size 2, so we pick minor CD. So the consensus group of A will be BCD and the window size is 3 now. With the design of PeloPartition, one region will have exactly one branch, and all of them will be merged after recovery, so we can save all transactions during the partition. In the next section, we are going to discuss some new threads introduced by the split and merge design. So the first thread is completing transactions. Transactions are selected from a mining pool to be included in the new block. Since the mining pool is not cleared after partition, miners from different regions can still pick the same transactions and include it in different branches, which will result in the conflicting transactions. So to solve this problem, we require all transactions to include the signature of first block in the branch as an identifier. So one transaction can only be included in one branch. The second one is one account used in different regions. Multiple people can use the same account in different regions, so they can spend all of the balance in multiple branches. It's similar to double spending. To avoid this, the wallet will be also partitioned when the chain is split. For example, in the branch with 1/3 of the consensus miner, one account can only spend up to 1/3 of its balance, so it cannot spend more than what it has across multiple branches. There are two more threads in our paper, inactive consensus miner and maliciously creating a branch without partition. So check it out if you are interested. Lastly, we will have the evaluation section. To evaluate the performance of PeloPartition, we run experiments on a blockchain simulator called SimBlock. We cut down the connections between America and other continents, so there are two regions. America has 1/3 of the total hash power, while the others has 2/3. First, we will show how PeloPartition behaves under different events. The axis here is a time series. Network partitions happens around 8 hours, while it recovers after around 16 hours. The y-axis shows the number of blocks of each branch. We can see that the main chain split into two after partitions. The growing rate of America, the red line, is half of the rate of the others. After network recovers, the two branches merge into one, and the new block generated in both branches are included in the main chain. Then we are going to compare the performance of PeloPartition with traditional blockchain like Bitcoin. The x-axis here is still the time series, but for the y-axis, we show the number of wasted blocks, which are blocks that are mined but not included in the main chain. So the red line is PeloPartition. We can see few wasted blocks because some blocks are competing for the signing procedure, but there is no change when the network recovers. For Bitcoin, around 15 blocks are instantly wasted after the network recovers because all of the blocks from the shorter branches are dropped. In conclusion, PeloPartition is a blockchain system that can tolerate network partition. The main goal of it is to preserve all works during the network partition while still ensuring the integrity of the ledger. So this is the end of our presentation. Thanks very much for your listening.